Wonderful. So I believe we have actually two of the authors here to answer questions. Xiaosong Ma, who just enabled her video, is a principal scientist at Qatar Computing Research Institute working on graph systems, storage, and cloud computing. And is Kang still on a panelist?
Yes, I'm here.
Oh, yes, great. So Kang is also here, who is a PhD student from Tsinghua University, and his research interests include graph computing systems and graph databases. So I believe we can start off with a question from Slack. Natalie, if you want to ask it on behalf of the...
Yeah. Okay, so this question from Slack says, nice observation and practice. Did you observe performance deterioration when the graph is highly skewed? Specifically, hot vertices might not be able to fit into the memory hierarchy and low degree vertices cannot be packed together easily. It doesn't seem intuitive how FlashMob deals with skewness.
Let me start with this question. So actually, skewness here is the exact blessing for this work. We actually thrive in skewness. It's based on the existence of such skewness that we can try to optimize in different ways for the high degree and the low degree nodes separately. For the high degree ones, because the problem is that they are visited so often, but their visit was never organized or batched with the existing way of random walk implementation. So what we did is that we still don't know who is gonna visit them, right, at each step, but we know many people will be there. So what we do is that we take each of this vertex and then pre-generate thousands or tens of thousands of selected edges. While we do this, although this vertex is large, has a large edge list, that can fit into the cache much more easily. And then we can use the data many times. And then once we have pre-generated these edges, when they are actually visited by the workers at at every step, they can just sequentially consume these edges, and then which bring much more efficient sequential accesses. And then the vast majority of nodes are actually low degree, but then they are visited much less. So with them, we just pack them together. With thousands of nodes now sharing the same degree, the data structure becomes much easier, and then the access becomes much faster. Hope that answers the question.
Thank you. Yes, and we have a question from Lushu. Oh, sorry, you actually muted. There we go.
Hi. I just, first of all, I like this work. Second of all, my question would be, because I don't work on graphs, so I would like to know if you can provide any insight on which of the techniques you just described would provide greater benefits for what kind of application. So specifically, I think you described two techniques on, you handle high degree vertices and low degree vertices differently. And I assume that you're making combination of these two techniques in your approach. So could you provide an insight on what kind of application would benefit from, one side of these techniques more?
So in general, we think this may apply to applications beyond graph random walk, because if you have, for example, a very uneven data accesses, right? Where you have accesses to a lot of hotspots, but these hotspots data, you cannot access them sequentially. And
right.
Then you have a large area of data that are accessed very sparsely. We believe that in real life, the distribution of access patterns or our daily activities often reflect this scenario. So in that case, what we did is basically by reordering the operations, we changed these high popularity data items access from not only hot, but to sequential. I think that's the main lesson we've got from this work, and we hope that they can apply to applications beyond graph random walk.
So basically, are you saying that most of the application that you basically apply has the similar sort of access patterns, so that I think they would benefit from both of these spectrums equally in a sense.
In the realm of graph random walk, there are large collection of algorithms, and we believe this approach will apply to them, all of them, because no matter what random walk algorithm you pick for graphs, typically you have this degree-based popularity distribution.
Right.
Yeah.
So, sorry to ask a follow-up. So, because what I understand was you only have limited space for caching, and obviously you can when you have to make compromises, if you have a huge graph, then obviously you want to maybe lean towards one side of the spectrum than the other. So based on what you just said, does that mean even with all these different kind of applications with different sort of access pattern to the graph, you still sort of observe the same sort of access pattern that benefits both of these spectrum easily, and the trade-off is mostly the same among different sort of applications? Is that what you were trying to say?
Yeah. I want to make it clear that we didn't have to choose between these. We actually tried to design both of their processing in a cache-friendly way, but we did different things with them. And at the runtime, because the graph itself is so much larger than the caches, we have to partition them. But again, we partition them different ways at different sizes and apply different sampling policies with each partition. But then when we do each of them, we make our best effort to make the accesses as fast as possible by having better cache utilization.
Right. Okay. Thank you.
Hope that helps. Thank you for the question.
Okay, and we have one more question from Slack, which might be the last one we have time for.
Great. So this question asks, for graphs of different sizes and with different random graph walking algorithms, did you notice that your observation holds true that high degree vertices are more frequently visited than low degree vertices?
That seems to be the observation. We didn't do a full profiling, but the ones that we have observed so far does fit this rule. Because, I mean, if you think about it, it's kind of natural, right? The high degree vertices will have many more connections and make people come to them more often. And then if you are a low degree vertex, only through one or two nodes will you be accessed. And then it will be much less likely for you to be visited. So we actually found that, at least with deep walk, the correlation between the visit frequency and the vertex degree is very strong.
Okay, thank you so much, both Xiaosong and Kang. I think we need to move on to the next presentation, but we can of course continue the discussion.
Hello, hey. Okay, thank you, Ke.
Thank you.
So I think there's one question from the audience already. So Tianxiang, you feel free to open up your camera and ask your question.
Hi, I'm a PhD student from Hong Kong University. Thank you for giving this excellent talk. I think it is very interesting to have the idea of using the skewed graph access pattern to increase cache efficiency. So my question is, since the observation of this work is, I think it's kind of application agnostic. So I wonder if this idea can be exploited to other graph analysis systems to help further improve their efficiency. Thank you.
Yeah, thank you. This is a very good question. So generally speaking, I think our techniques can be applied to other graph sampling algorithms. But for the common or standard graph algorithms like shortest path or BFS, their memory access is already in a sequential way. That is to say, when you access an active vertex, like in the shortest path, all of its adjacent edges will be accessed in a sequential way. So that the memory access pattern is already good enough. So this is the different from the graph sampling algorithms.
Yeah, thank you.
All right.
So, Ke, I think that is very interesting work. So we actually it happens that we also about half a year ago we published a paper in VLDB 2021, and we call a system called Sander RW. Actually, we addressed almost the same problem, cache efficiency of the random walk. Actually, yeah, it's quite amazing that you to see your solution. We think differently. What you're working on is we trying to, I think, a very smart idea. So you are trying to opt the graph layout, and also then you take advantage of vertex with different degree. So and then customize them into different so-called walk calculation. So for large degree, you basically have a buffer. For small degree, you don't you can go straight or you do direct sampling. That is a very cute idea. So have you? I have one question here. Is that maybe two questions? One is actually the first one. How do you actually now you're trying to partition the graph according to degree, right? But in fact, if you look at the structure, I mean, basically you look at the vertex by one step, and then you're trying to optimize each step, right? But if you look at the random walk itself, is you have a lot of this random walk happen at the same time. So maybe it makes sense to have another matrix of partitioning. It's like, think about community, right? So probably, for example, if you look at community, then if you do the partition according to the community, then you may have a better temporal locality on this, right? Rather than just partition on the degree.
Yeah, sure. I also read your paper, Sander RW. I think that is a very great idea. I think you're using the step interleaving technique, and so for your question, I think you mean sort or partition the graph by the community.
Yeah, have
right?
you tried another approach to partition the graph? Basically, I want to understand.
Yeah, I definitely agree. So partitioning by the community will help a lot, because the spatial locality they are in this community, because the workers tend to work in this community. But one thing I'm not sure is how long it takes to do the pre-processing if we want to mining out this community. Then that might be. I think this is a great idea, but I'm not sure if this pre-processing time is affordable.
Yeah, you're right. Your current data format is very, the partitioning is very straightforward. I would say you don't need to have a strict order. Actually, you just have some kind of bucket is fine. You have a bucket sort, then it's fine. Yeah, very interesting work. And also, it's quite amazing. We come out with different approach to the same problem. Okay, anyway, so I think there's another audience raised their hand. Maybe Hao-Wen. I'm done. Hao-Wen, you go ahead.
Oh, hi, hello. I'm Hao-Wen from HBKU, and I think it's great work. I have one question regarding the pre-sampling. So it seems to me that the pre-sampling process assume that the random walk is stateless, so about the worker. So it doesn't consider the state of worker when doing pre-sampling. So it just sample based on the vertex, and so let the worker consume the sampled buffer sequentially. But I see in some random walks or other walks working program algorithm on graph that the transition probability is not only based on the current vertex, but also based on the state of the worker. So in that case, can pre-sampling still cope with this sort of sampling algorithm that is not only based on the current vertex, but also based on the state of the worker?
I think the question is more or less like, how do you support second order random walk, for example?
Yeah. This is a very good question. Thank you. So we have also evaluated a dynamic random walk as a second order random walk in our paper, that is a node 2x. Our solution like this. So the pre-sampling, it pre-sampled many edges. In this stage, this sampling is independent, is ignorant of the worker state, and we use the rejection sampling to do this whole so in the whole view, we use the rejection sampling, and in rejection sampling, you first sample an edge, and then you have a probability to accept it or deny it. So this edge sampling happens in the pre-sampling phase where the worker state is irrelevant. And when during the walk, when we're actually doing the rejection sampling, we directly fetch the pre-sampled edge in the buffer, and then we use the rejection to accept or deny it. So in this sense, our solution works even better in dynamic random walk, because in dynamic random walk with rejection sampling, the memory access has very high data dependency, because you don't know if you are going to reject or accept an edge before you sample it. So there is a high data dependency. But in our case, as the edges are fetched from the edge buffer sequentially, so this data dependency, the latency caused by this data dependency is very small, because the data are already in the cache.
Okay, thank you very much.
Sorry. One thing additional is that if you are interested in our paper, I definitely recommend you to also take a look at the standard RW published in the VLDB this year, in May, perhaps. Yeah, and they also proposed a very good solution to the random walk, addressing the random memory access problem.
Okay.
Yeah, in fact, our two approach can be combined together. It's also
Yeah, definitely. So the direct sampling can be combined with the step interleaving technique. Yeah.
Okay, I will look into it. Thank you.
Thank you.
Great. Oh, awesome. Looks like we got some potential collaboration that happened during the talk. That is awesome. All right, okay, so due to time limit, we have to move on to the next talk, but we will have all the authors stay back for the panel discussion later. So if you have more questions, definitely welcome to ask more. Okay, so for our last talk of the session,